Good morning, all of you. Today we shall discuss about the deduction of a generalized formula for the total number of possible derangements on a given finite set. Suppose we have n distinct letters in our hand which are denoted by L1, L2, to Ln. Suppose L1 is destined to reach the address A1. L2 is destined to reach the address A2. L3 is destined to reach the address A3. And finally, Ln is destined to reach the address An, where A1, A2, A3, to N are all distinct. We shall have to try to find out a generalized formula for the total number of possible derangements on the set of these n letters. Let Dn denote the total number of possible derangements on the set of these n letters, n distinct letters, L1, L2, to Ln. Now, we shall deduce a generalized formula for Dn. So we proceed as follows. Since it is a derangement, we must have a total mismatch. In other words, no letter should reach the correct destination. That means we must have, for a derangement, we must have L1 does not reach address A1, L2 does not reach address A2, L3 does not reach address A3, and finally Ln does not reach address An. Now let us focus our attention on this particular letter L1. Since it is a derangement, L1 cannot reach address A1, but there are two possible cases. L1 may interchange its destination with any one of the remaining n-1 letters, or else there is yet another possibility. In this case, L1 goes to some other address, but it does not interchange its destination with any one of the remaining n-1 letters. Yet we have a derangement. So, first of all, let us see case 1. Suppose L1 interchanges its destination with letter Lm, where m is not equal to 1. In other words, we can say L1 goes to m and Lm goes to A1 where m is not equal to 1. Now since it is a derangement, we must have a total mismatch. Therefore, we must have some additional requirements. That means we can say that we must have Li does not reach Ai for all I not equal to 1 comma m, where I belongs to the set 1 2 dot 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 to n, or 1 less or equal to I less or equal to n. Now let us see. Actually, in this case, the problem in fact reduces to the problem of determination of the total number of possible derangements on a set of n minus 2 distinct objects. Actually, the total number of derangements on a set of n minus 2 distinct objects is nothing but dn minus 2. Now L1 may interchange its destination with any one of the remaining n minus 1 letters. Therefore, the total number of possible derangements in this case must be equal to n minus 1 into dn minus 2. Now let us focus our attention on case 2. In this case, L1 reaches some other address, but L1 does not interchange its destination with any one of the remaining n-1 letters. Suppose L1 goes to AK, but LK does not reach A1, where K never equal to 1. And since it is a derangement, we must have some additional restrictions which I mentioned below. Actually, we must have Li does not reach Ai for all I not equal to 1 comma k, where 1 less or equal to I less or equal to n. So over here we have exactly n minus 2 restrictions, and besides that we have an additional restriction over here, which is this one, that LK should not reach address A1. So in this case, the problem reduces to the determination of the problem of determination of the total number of derangements on a set consisting of n minus 1 distinct objects. Now L1 may reach any one of the remaining n minus 1 addresses. So the total number of possible derangements in this case must be equal to n minus 1 into dn minus 1. Therefore, if we combine these two cases, we get the total number of possible derangements on the set of these n distinct letters, which must be equal to dn, and thus we have dn is equal to n minus 1 into dn minus 1 plus n minus 1 into dn minus 2. And this recurrence relation must be true for all n greater or equal to 3, where n is any positive integer. So we see that dn must be equal to n minus 1 into dn minus 1 plus n minus 1 into dn minus 2 for all n greater or equal to 3. Therefore, we can write dn is equal to n into dn minus 1 minus dn minus 1 plus n minus 1 into dn minus 2 for all n greater or equal to 3. Therefore, we can write dn minus n into dn minus 1 must be equal to minus common dn minus 1 minus n minus 1 into dn minus 2. And this recurrence relation must be true for all n greater or equal to 3. Now previously we have seen that d1 is equal to 0 and d2 is equal to 1. Therefore, d2 minus 2 into d1 must be equal to 1 minus 2 into 0, and that must be equal to 1 minus 0, which is equal to 1, and that should be equal to minus 1 to the power 2. Now whenever we substitute n is equal to 3 in this relation, we get d3 minus 3 into d2 must be equal to minus common d2 minus 2 d1, and that must be equal to minus 1, and that must be equal to minus 1 to the power 3. Similarly, if we substitute n is equal to 4 in the above relation, we get d4 minus 4 d3 must be equal to minus of d3 minus 3 d2, and that must be equal to minus of minus 1, which is equal to 1, and that must be equal to minus 1 whole to the power 4. We continue in this manner, and finally for any n greater or equal to 2, we must have dn minus n into dn minus 1 must be equal to minus 1 to the power n. And this relation, this recurrence relation must be true for all n greater or equal to 2. Now we divide both sides of this recurrence relation by n factorial. Then what do we get? dn minus n into dn minus 1 divided by n factorial must be equal to minus 1 to the power n divided by n factorial for all n greater or equal to 2. Therefore, we have dn by n factorial minus dn minus 1 divided by n minus 1 whole factorial, and that must be equal to minus 1 to the power n divided by n factorial, and this recurrence relation must be true for all n greater or equal to 2. Now let us substitute n is equal to 2 in this particular relation. So for n is equal to 2, we get d2 by 2 factorial minus d1 by 1 factorial must be equal to minus 1 to the power 2 divided by 2 factorial, and that must be equal to 1 by 2 factorial. For n is equal to 3, we must have d3 by 3 factorial minus d2 by 2 factorial, and that must be equal to minus 1 to the power 3 divided by 3 factorial, which must be equal to minus 1 divided by 3 factorial. For n is equal to 4, we must have d4 by 4 factorial minus d3 by 3 factorial, and that must be equal to minus 1 to the power 4 divided by 4 factorial, which must be equal to 1 by 4 factorial. So we continue in this manner, and finally for n is equal to n, we must have dn by n factorial minus dn minus 1 by n minus 1 whole factorial must be equal to minus 1 to the power n divided by n factorial. Now let us add up all these relations. So actually what do we get in this case? dn by n factorial minus d1 by 1 factorial, and that must be equal to 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus dot 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 dot, and finally plus minus 1 to the power n by n factorial. But d1 is equal to 0. Therefore, we can write dn by n factorial is equal to 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus dot 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 plus minus 1 to the power n by n factorial, and this relation must be true for all n greater or equal to 2. Therefore, if we multiply both sides by n factorial, we get dn is equal to n factorial into 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial plus dot 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 dot, and finally plus minus 1 to the power n by n factorial, and this relation must be true for all n greater or equal to 2. And finally we also have this one, actually d1 is equal to 0. So these two relations in fact constitute the generalized formula for the total number of possible derangements on a set of n distinct objects. If you think that my video is interesting, then please subscribe my channel. In my next class, I shall discuss about some other problems related to combinatories. Thank you very much.